So I think we have already learned, okay? We have already learned LCR measurement using bridge. Now voltage and current measurement using analog instrument. Okay, so these two parts we have completed. Okay, so we have learned one technique, that is de-Arsenal setup. Okay, so we see uh, how to develop a de-Arsenal setup to measure voltages and current. Basically, we can measure DC and AC current using that setup, but using a rectifier. Okay, by adding a rectifier, bridge rectifier, we can modify this de-Arsenal setup to measure AC current also, AC current and voltage also. Okay, so basically we can measure DC current and voltages. Okay, but by applying a rectifier, we see how to measure AC current and voltages. I think now you are okay with that. Okay, so do you have any problem related to those we have learned?
No, sir.
Okay, just
Regarding
refer, yeah,
DSL,
just refer the reference book and do the example I have highlighted. Okay, then that is okay. And also do my assignments, the tutorial questions. Okay,
okay.
then that's knowledge will be enough for your final exam. Okay. Okay. So actually we are in learning outcome one. Okay. Still we are in learning outcome one. Okay. LO1. Okay. Uh, Actually also we need to learn the digital instrumentation. Okay. Digital instrumentation. Okay. So we will see one techniques which is used for digital voltmeter, that is RAM techniques. Okay. Okay. So if you consider digital voltmeter, okay, if you consider digital voltmeter, okay, uh, so um, so so there are various features, okay, with digital voltmeter, okay. So those are these features, okay. So you can see them, okay. So and also there are some techniques, different type of techniques used to implement digital voltmeter, okay. So this is one techniques, okay, RAM techniques. This RAM techniques is used to implement digital voltmeter, okay. So we will see what is the theory behind it. And I think before going to the digital instrumentation, okay, so it is better to know some items related to digital domain, okay. Uh, So one is this one, analog to digital converter. Okay. So have you any idea about this component, ADC? What is ADC? Analog to digital converter. What is that? What is the purpose of it? So it convert analog signal, analog to digital converter. Actually, the primary task of the analog to digital converter is converting analog signal into a digital signal. Okay, digital signal. Maybe in signal and system, you uh, you learn this stuff. Okay, so there are three main process. Three main process. Okay, that is sampling, quantizing, and encoding. Okay, so these are the three main uh, process involved with analog to digital converter. Okay, so implement of analog to digital converter is very easy actually, using op amps Op-amps, okay. Op-amps we can use to compare voltages, okay. Op-amps we can use to compare the voltages. So we can use op-amps as a comparator, okay. Comparator, then using this comparator, we can use comparator and op-amps and actual resistors, okay. Resistor ladder, you need a resistor ladder. Using op-amp and resistor, we can easily implement ADC, okay, analog digital converter. That is the most basic one, okay. But there are other techniques also, okay. SAR techniques, okay. There are other techniques also to implement ADC, okay. So no, we are not going to implement. We are not going to see the implementation of ADC here, analog digital converter here, okay. Actually, that is related with digital electronics, okay. So if you need, I can share some videos related with the analog digital converter, okay. But that is only for knowledge, okay. Not the exam question will not come from this part, analog digital converter, okay. So it is not our actually these instruments are in our LOs, okay. We have to learn these things, but not deeply, okay. We no need to learn the design of ADC, but we should have a simple understanding, okay. So if you consider ADC, analog digital converter, okay. So we know that I will these things I have no time to explain, okay. So I will quickly explain, okay. So normally real world is analog. Real world is analog. The world is changed as analog, okay. The amplitude is continuous. Analog means amplitude is continuous, okay. That is analog. That is the meaning of analog, okay. So real world is analog. For example, temperature variation, that is analog, okay. Our voice, that is analog, okay. So continuously varying, okay. And height of a tree, the growth of a tree, that is analog, okay. So the variable is continuously varying, okay, not discrete, okay. So these are analog signal, okay? So normally real world is analog, okay. But if you want to process this real world parameter in digital system, basically we need to convert this analog signal, analog information into digital form, okay. So that is the primary task of ADC. That is a primary task of ADC. Okay, that is a primary task of ADC. Okay, so what it do is, okay, first it take the analog signal, then it sampling. Okay, that means it take some sample here. Okay, so this is most probably this is a time varying voltage. Okay, this is a time varying voltage signal. Okay, so you know that if we use a speaker will convert our sound into a voltage signal, time varying voltage. Okay. So we take that sound, the electrical signal, and we get some sample. That means we are getting some voltage value. Okay. So we are getting some voltage value. So those voltage value may be 2 volt, 2.5, 2.75 volt, likewise. Okay. Then, so once we get the sample, we will get this kind of discrete signal. This kind of discrete signal. Okay. These are samples. Okay. These are samples. Okay. And discrete signal here and here the independent variable is t. Here independent variable is normally n. That is the number of samples. This n is related with time. Okay. This n is related with time. Okay. Actually, time is equal to the number of sample, the sample number into sampling time. Okay. So this n is related with time anyhow. Okay. So we no need to go much further. Okay. So anyway, we are getting like this samples. Okay. Then the next process is quantizing. Quantizing means, okay. So if you consider ADC, okay. So ADC can give a voltage value. Voltage value can represent analog voltage value using several bits. Okay. So some ADC use 4 bits. 4 bits. Some ADC maybe use 8 bit, some ADC maybe use 16 bits. Okay, this is we call the resolution of the ADC. This is we call the resolution of the LCD, ACD, resolution. Okay, resolution of ADC. Okay. So resolution means the number of bits which used to represent the voltage value. Okay, so for example, if you get two bits to represent voltage value, that means there are only 4 levels you can represent: 0, 0, 0, 1, 1, 0, 1, 1. Okay, so only 4. Okay, only 4. What happened? Only 4 voltage level you can represent. Okay, so let's say that your signal is uh, 5 volt, 5 into 5. Okay, so your signal is 5 volt signal. Okay, so that means, so you have to represent 0 to 5 voltage value only using these four levels. Okay, so you can't show all the voltages value here. No, from 0 to 5 volt, there are infinite number of voltage value: 0 0.1, 0 0.0001, 0 0.0001, 0 0.2, 2.001. Likewise, we can't count the number of levels. Okay, so that is why it is continuous. Okay. Okay. So there are infinite number of values between 0 and 5, but only you can represent only 4 values. So that means maybe you can represent 5 divided by 4, that is 1.25. Okay. Okay, these are the levels you can see. Okay, then you can using this, you can show 0. Here you can show 1.25. Here you can show, yeah, I think you need to divide this by 5, 4 minus 1. Okay, 3. 5 divided by 3. 5 divided by 3, it will be 1.7 around. No, 1.7 around. Okay, so you can show only 0 voltage, 1.7 voltage, 3.4 voltage, then 5. Okay, so these are the voltages value you can show. Okay, only these voltage value you can show. Okay, so what you have to do, you have to get the maximum voltage, and you should divide it by 2 into the resolution. N means the resolution, that is the number of bits which represent the voltage values, that is the resolution. Okay, then minus 1. Then you will have the smallest voltage level you can show. Okay, so there are only 4 levels. Okay, so now you can see that here there are many levels. Okay, there are many levels. 0 to 5, there are many levels. Okay, so then you have to approximate these levels to these 4 levels. You have to approximate that levels for 4 levels. For example, if you have 0.001 voltage value, you have to approximate it to 0. If you have 1.69, you have to approximate it to 1.7. Okay, so you have to approximate. That approximation is referred as quantizing. Okay, that approximation is referred as quantizing. Okay, then after quantizing, you will have only these the finite voltage levels. Okay, so that finite voltage value can be represented using the bits, number of bits. Okay, 1 and 0. That is we called encoding. Okay, so that is the process of analog to digital conversion. Okay, I'm sorry, I have to quickly tell you. Okay, otherwise we don't have time. Okay, because we have only 2 weeks. Okay, for the lectures. Okay, we have to cover something. Okay, so we have to go quickly. Okay, so anyway, there is no question. Maybe you have to explain the analog to digital conversion the purpose of ADC and what is the resolution of ADC. So those kind of question may be come. Okay. So those are very easy. Okay. So you should understand those things. Okay. Related with the ADC. Okay. So there are mainly three processes. Sampling. Actually, sampling we learn in signal and system. Okay. And also digital signal processing. Sampling, quantizing. This quantized signal is called as PAM signal. Maybe you can remember this is called as PAM signal. Okay. Then encode. Okay. So these processes are there. Okay. So I think you have idea what is sampling, what is quantizing, and what is encode. Okay. Sampling means getting a sample voltage value. Quantizing means approximate it to the uh, uh, voltage level that can be represented by a binary form. Okay, represent in binary form. Then encoding means representing the quantized voltage level in binary form. Okay, so that is ADC. Okay, and also there are, so that is one part. Okay, and there is another part that is DAC. That is DAC, digital to analog converter. Digital to analog converter. Okay, so these are available. These are electronics component. Okay, these are not much expensive. Okay, very simple electronics component. We can buy in an electronic shop. Okay, ADC, DAC. Okay, so DAC also the vice versa of the ADC. This convert the digital signal into analog form. Okay, digital signal into analog form. That is why it is called DAC, DAC, digital to analog converter. Okay, digital to analog converter. Okay, so there are many type of DAC. Okay, there are parallel DAC, serial DAC, as well as parallel ADC, parallel DAC, likewise. Okay, and the parallel DAC easily can be constructed using only resistors. Actually, using only resistors, we can develop a parallel DAC very easily. Okay, so that is not much difficult. Okay. So voltage levels are there. Okay. So resistors can be used as a voltage divider. Then we can use resistor ladders. Okay. To develop DAC, digital to analog converter. Okay. So you should have that idea also. What is a DAC? Okay. That. Okay. And other part, so these components are widely used in digital instrument. Okay. Analog to digital conversion and digital to analog converter. Okay. Okay. Other one is counter. What is a counter? Counter can count the number of pulses. Okay. So counter can count the number of pulses actually. Pulses. 0 and 1s it can calculate. Okay. So this is actually the sequential logic circuits. Okay. So that can be made using flip-flops. Okay. Okay. We can construct this counter using flip-flops. Flip-flops are sequential logic circuits. You know it already. Sequential logic circuits means we need the clock data to operate that logic circuit. Okay. So some logic circuits doesn't need a clock signal. That is we call combinational logic circuits. Okay. So these counters are sequential logic circuits. Okay. So there are many type of counters. Okay. Serial counter, parallel counter, up counter, down counter. Okay. Maybe you can see them. Okay. So just have idea what is a count. Okay. So maybe you can refer internet to find more details, and also maybe I also have recorded some session related with counter implementation. If you need, you can refer those videos. Okay. So it is in my channel. Okay. So you can see them if you need. But these parts will not come to the exam, much difficult. thoroughly, okay? The construction will not definitely come. You should have the operation, the function, and the use of this instrument, okay? Component, okay? That is in, okay? No need the design things, okay? But if your knowledge, if you need, you can see them, okay? So that is an analog digital converter, digital to analog converter, counter. Another is register. Registers are also sequential logic circuits using flip-flops. Okay. So this is a memory actually. This is a memory. Okay. We can store some bits in registers. Okay. So this kind of instrument may be needed for uh, develop digital instrumentation. Okay. So here you can see that the counter is there for a RAM type DVM. Okay. RAM type DVM counter is there. So if I show you a common voltmeter architecture, okay. So I will write and type digital voltmeter diagram, maybe. This side. Okay. So you can see that there are very comprehensive things are there. Okay. So this is actually the common block diagram of a digital voltmeter. Okay. Uh, there is a display. Okay. And the generator and gate. Okay. I think this one. Yeah. Yeah, this one. Okay. So here you can see that. Okay. Digital voltmeter. Uh, Actually, it is not. It is just the analog to digital converter. Okay. It is just a ADC. Okay. The main part is ADC. Okay. Digital voltmeter. The main parts is ADC. Okay. And so actually, digital voltmeter. The digital voltmeter can be classified based on the ADC conversion. Okay, so there are many type of ADC conversion, analog digital conversion. Okay, so the digital voltmeters are mainly based on the analog digital converter. Okay, so that is why I told you that for the digital instrument, these are very important component. Okay, so ADC. Okay, so this is a simple block diagram of uh, voltmeter. Okay, so this input signal, that is a volt. Okay, so attenuator is there. So attenuator is there. That is this ADC will support up to some level. Okay, so attenuator is used to protect this ADC. Then it convert the the voltage into a digital form. That means 1010 stream. Okay, so using a counter, we can count that 1010 stream. Okay, So then that count can be made to proportional to the, can be made of proportional to the, to a voltage value. Then you can read it, you can show it, okay? So readout system means we have to map this counter value with the voltage value, okay? So there should be a proportional mapping. Then we can see the signal in the display, okay? So this is the basic idea of a digital voltmeter, okay? Maybe better you note this one, okay? Because this is not in our uh, reference book, okay? So maybe you can note this one, okay? So, so our voltmeter are classified, can be classified actually mainly based on the analog to digital converter, okay? So if we go to our reference book back, okay? So I will explain what is ramp technique, okay? Okay, so you can see that, okay, for a voltmeter, analog to digital converter, counter are the main components, okay? Those are the main components, okay? So now it is like this, okay? So we have a signal, we have a voltage value, some voltage value here, okay? Then what we do is we are generating a signal, okay? So we are generating a signal from some high value to low value, okay? So your voltmeter value, voltmeter range mainly depend on this voltage value, okay? So this is we call the ramp signal. Ramp signal means it is continuously increasing or continuously decreasing linearly increasing or linearly decreasing signal. That is we called as a ramp signal, okay? Maybe in signal and system you have learned this, okay? So ramp signal is like this, okay? Y equal mx plus c. If any signal is following this one, y equal mx plus c, then we call it a ramp signal, okay? So this is also related with y mx c. Here the m is minus value, okay? And c is plus value, okay? For this signal, okay? So this is first from high to low, it changed the voltage, okay? Then once it equal to this voltage value, okay? So let's say that we have some voltage value, we input value. Once the voltage, this V in, this is the given voltage, is equal to this voltage, that is the voltage generated by the unit, okay? So there should be a signal generator. There should be a signal generator, okay? So that signal generator signal is equal with this voltage, okay? Okay. So that voltage is marked. That voltage is marked here, okay? So how we can detect this voltage? So very simple methods you can use to detect that voltage, okay? That means if you have, for example, let's say that you have a 5 volt is appear, okay? 5 volt is appear in the voltmeter terminal, okay? Now you are generating 5 volt. You are generating, so you are decreasing the voltage value from some point to some point, okay? So let's say that this voltage is plus 5, okay? This voltage is plus 5, okay? Then you 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 you, for example, it is like this, okay? We can, let's say that we have a voltage value here. Then this ramp, the generator voltage, we can connect other side, okay? For example, if we have a like this battery, okay, 5-volt battery, okay. So see, this signal generator can be connected as other side like this. Okay, serial. Okay, so this is 5-volt is there, and your signal generator is connected like this, other way. Okay, so when this is high volt, let's say that 12-volt, then 12 minus 5, it will be 7. Okay, so 7 voltage is there. Okay, now you are decreasing that, this 7 is decreasing. Okay, once it's come to 6, this will be 1 volt, the difference will be 1 volt. Once it's come to 5, this difference will be 0. That 0 point you can detect. That 0 point you can detect. For example, if you connect this 0 point to a transistor base, okay, like this, okay. And when this terminal is 0, this transistor, if you use this as a emitter, this is a collector, and this is a base. Okay, so this is just you can use as a switch. Okay, so once this base current is not there, base voltage is not there, this transistor is cut off. Okay, so you can detect this voltage, so that you can detect this voltage. Okay, so that is one method, one simple method. Maybe that method may be not used in voltmeter. There can be many advanced method. Okay, but I just tell you that we can detect a voltage like this. Okay, we can detect a voltage like this. Okay, then again we decrease it, then again increase it. Once it is increasing again, that voltage, once the voltage level, the input voltage level is equal to this generated voltage, again it can also be detected. Okay, okay, that means this time and this time, the time you can count using a counter. Maybe you can count this time from here to here and from here to here. Okay, so if you know this function, that is y equal mx plus c, if you know this function and if you know the time, okay, so using this function you can calculate the voltage. You can calculate the voltage value here very easily using this function. Okay, so that is the principle of the uh, ramp type voltmeter. Okay, maybe you couldn't understand it properly. Okay, so what you understand is, okay, in RAM type, we are generating a RAM signal. Okay, so that RAM signal is starting from high value to some lowest value. Then again, it is increasing. Okay, so once is decreasing and increasing. Okay, once this ramp generator voltage is equal to ramp generator voltage, we say that V ramp. Okay, so once this V ramp is equal to input voltage, that is the voltage to be measured. This is the measuring voltage to be measured. Okay, so it is detected. It can be detected. Okay, so one simple method I have suggested here. So that may be not the efficient one. Okay, this may be not the efficient one, and this is just a joke. Okay, this may be a joke, but somehow we can implement like this. Okay, so there can be many advanced method. Okay, compared with those advanced method, this can be a joke. Okay, but still we can use it. Okay, maybe not efficient. Okay, so once that voltage is equal to the measured voltage, okay, that one is marked, again it decreased up to level, again increase. Okay, again it cross this voltage, when it equal to the input voltage, that one is also marked, can be detected. Okay, then if you know this function, using the time to reach this point and time to reach this point, we can calculate this voltage value. Okay, using this function, Using this time, you can calculate this voltage value. So that is the RAM technique. Okay, that is the RAM technique. Okay? So I think that is enough for the RAM type signal, RAM type uh, one. Okay, so maybe there is no uh, so so that is one method. Okay, so I think so no any mathematical calculation will not come. Okay, but maybe this function may be given. Okay, and time also may be given from here to here. Then maybe you will ask to calculate the voltage value. Okay, so that kind of simple. Okay, in I think in grade 7, grade 6, we learn those things. Okay, so if we know the function, if we know y equal mx plus c, then if you know this time value, if you know the time point 2, okay, if you know the time, this is a time. Okay, this is a time, this is a time. Okay, so using so we can calculate that time easily. Okay, okay. So anyway, that time is calculated in so this is the time. Okay, this is the time. Actually, they calculate the time from this to zero. From this to zero time they calculate. Okay, using a counter. Using a counter. Actually, once this when this point is detected, the clock pulse is on. Okay, so you can calculate this clock pulses using a counter. Then you can calculate the time. Okay, so counter can be used to calculate this clock pulse. Okay, so maybe if you know this time value, if you know the time, okay, using that time you can calculate this voltage. Okay, so that kind of question maybe can come to you. Okay, so I think no need to do any example. Do you want any example? For example, if I ask you like this, okay, so for a specific RAM type signal, okay, the RAM signal is generated y, sorry, v equal minus 3t plus 12, this decreasing one, and this one is v equal 4t plus 40 minus 5. Okay, so I have given uh, uh, two voltage, two ramp signal. Okay, so one is this one, another one is this one. Okay, this is time. Okay, so here you are starting from plus value, then you are coming to the minus value also. Okay, so let's say that you have detected the voltage equal at this point. This point. Okay, so maybe I have given this time value. Time value is maybe 5 seconds. Okay, so if I give you the 5 seconds, then using this equation, you can calculate the volt, no? So what you have can calculate, you can simply add 5 seconds here, then 3 minus 3 into 5 plus 12. So that means, so that can be 5 actually, maybe that can be 2. Okay, so it will be minus 6 plus 12. So voltage is 6 volt. Okay, so you can calculate the voltage here. Okay? So maybe I can give you like this. Okay, I can give you the time duration from here to here. That duration is 3 seconds. Then how you can calculate? Okay, so you can calculate. Okay, this is the duration. This is a volt. Volt divided by duration. That is the that is what that is the gradient. this one, minus 3. Okay. So using this equation, you can calculate the volt. Okay, if we give you the duration. Okay? So simple way. There are simple ways. So that kind of question may become, okay. So very easy. Okay. So you no need to keep remember this DVM block diagrams. Okay. Anyway, the exam will be a open book one. Okay. So anyhow, you no need to uh, keep remember. Okay. So that kind of question will come. Okay. Okay. So I think that may be enough for DVM. Okay.